Have you been to this kind of ride before? I'm pretty sure you did. This is quite common in different theme parks around the world. So when I was queuing for this machine, I had a physics question, and that is, what will happen to a heavier person if he or she is riding on this? Would that make a difference comparing to a lighter person? So for example, would that person make a greater angle or maybe smaller angle comparing to another person? So maybe from the angle, then we can somehow estimate and compare, different riders' mass. So that's the question that I would like you to figure out today. When the physicists try to analyze a situation, we usually build a simple model from the reality. So here is a diagram that pretty much is the model that you can rely on for the ride that I just mentioned. And this is also the example 6.6 that we would like to go through as well. So for now, if you're confident, you can go and pause this video and try to work out the equation yourself. If you don't feel that you have the idea, you can continue with this video and pause at any time that you start to have the idea.
A few moments later, a few inches later, 2 hours later, 1 eternity later.
Alright, so far you have actually seen earlier a vertical circular motion where we talk about looping the loop. You also have seen horizontal circular motion where we talk about example 6.5, talking about the car making a turn. In this common example, is still a horizontal circular motion. However, the force is a bit tricky, right? You can see it's not just a horizontal, like it's not on the same plane. So that's why later on we'll need to deduce the equation vertically and horizontally, just like how you do in chapter 2. To solve this kind of question, the first step is always draw the free body diagram. And so we will need to draw here with a weight because that's is a mass. At the same time, you can see this is connected with a string, and therefore there must be a tension here. So if you really want to get this in scale, you may want to get the vertical component of the tension to be the same length. I think I could draw a little bit longer. Okay, so then the vertical component of it will be somewhat the same length as the weight, because vertically we could actually call, these two are the forces, by the way, that's all. And so we have weight equal to the vertical component, Ty, we could say, but then writing down Ty is not really meaningful. We will rather look at how we can express it with the angle theta here. And so if you look at this configuration, then you should be able to see this is theta, because this is like this vertical line is like the parallel line. So you can find the alternate angle, this is theta. And so in this case, then you can see this should be cosine. Not L, by the way. L is just the length of the string, so it should still be T. T is a force. Cosine theta, then that is how it could be expressed vertically. And so obviously for the horizontal force, okay, by the way, when you draw free body diagram, then you should not draw the component. But then here, just for my own reference, then I could write down here as T. Since it was cosine, then this one must be sine theta. And so if you look at, again, overall in the whole picture, this is the only force that is going horizontally, and that's the force that maintains its motion. So I can write down horizontally, then F, because it's doing circular motion, F equals to ma for circular motion. C stands for centripetal force. So then we have T sine theta equals to ma. You can, depends on what situation, what kind of question you are facing. And so here I'll just name it as v squared over r for simplicity. If you need to calculate something else, then you can use a corresponding equation. And so you may say that's pretty much what the question asks you to do. In fact, you can do one more thing, alright, and that is if you have these two equations, so equation 1 and equation 2, you can somehow simplify and deduce some more stuff. And that is, I will do equation 2 divide equation 1. Okay, I'll let you know why. Because if you do that, then you can have from equation 2 t sine theta divide t cosine theta, which would look really good. And then the other side will be mv squared over r divide the other side, which is the weight. Let me just put it as mg. So the best thing of this is you can then cancel out the t, you can cancel out the m, and then you can simplify the equation. I assume you have learned this in maths. Sine divide cosine will become tangent. So tangent theta equal to v squared over r. This g should go underneath, okay, right here. So that is a new expression you can derive. The interesting thing about this equation is you can see the m got cancelled out, and so that is to say, no matter what mass you are having, then the angle that you have will be the same as long as you are having the same v, same r, and same g. So yeah, this is a very interesting fact. However, if you want to deduce the relationship between theta, v, r, and g, you got to be more careful and more conscious about the physics. So let me show you some idea. For example, you may think that, hey, if we increase the v, so if it spins faster, while keeping r and g constant, what will happen to the angle? So from this mathematical relationship, you may see that, okay, so angle should increase just by looking at this equation. And that actually makes sense, because if you think about, let's say at the beginning, the chair and the string or the chain will be vertical before it starts to spin. And so when it starts to spin, it go, with greater and greater angle. So that kind of makes sense. At the same time, if you think about another scenario, if v remain constant while g go down, let's say, mathematically you should also increase the theta. And that is, you can imagine if you somehow can move the ride to the moon, then it seems like it can spin, with greater angle when you're maintaining other things the same. So that seems to make sense. But then when you start to think about the radius r, then you can think about increasing, for example, increasing or decreasing. It doesn't really matter. So increasing or let's do decrease. Decreasing r, then it sounds like it would increase the angle. But then if you try to put a second thought onto this, it's a bit strange. Think about this. When you decrease the radius somehow, right? So maybe you go like this, your angle would definitely be decreased as well, because that's the relationship that they have, like, geometrically. So it doesn't make sense when you have less radius but then greater angle. That's pretty much impossible. Greater angle must go with greater r. So I think this is a very good example to show you the way that you deduce the relationship of, from an equation in physics. You can't just look at the mathematical relationship. You also have to see whether or not these variables, so here are 4 variables, v, theta, r, and g, whether or not they would be independent to each other. And that's very important, because for g and v, they actually can change without changing the angle itself. So that was okay. But then if you look at r, then it is not. R and theta actually is dependent on each other. So the way to analyze this better is to change R to be something else. So what you can do instead is maybe think about the geometric relationship of R with L instead, and that is R equals to L sine theta by looking at this angle. And so you can now rewrite the equation as L sine theta tangent theta equals to v squared over g. And so the interesting thing is, sine theta and tangent theta, they are both increasing function from 0 degree to 90 degree. All right, increasing function means they always increase within this range, and so it will be so easy because we don't have to deal with angle with larger than 90. That would be like something like that. That is, I think, out of our scope here. And so for L, which is the length of the string, we can then think about, hey, what if it is shorter or longer? So let's say if the string gets shorter, then since this is going to be constant, then the only thing that happened will be sine theta times tangent theta got to be bigger, and that means each of these, right, or you may say the angle simply, will become bigger also. Okay, so that means if you have a shorter length for the ride itself, then with the same speed of rotation, same planet, then the angle has to be greater. So let's say you somehow have a string, so one string is like this, another string will be like this, they both go at the same time, then the one shorter and higher up will have a greater angle simply. So that is the solution that we can talk about. But then for radius, because again it changes with the angle, so you can't really comment on how radius affects the angle because they just dependent on each other. So that's all for this example and also the question about the flying swing ride. So I hope next time when you try to go to theme park, other than having the excitement and joy for playing around, also try to think about physics. I hope you enjoy learning physics with me. If you do so, please hit the like button now and subscribe to my channel. I'll see you again in the next video. Bye.